Hello and welcome to this presentation on a study of salient modulation domain features for speaker identification by Simon McKnight, Aidan Hogg, Vincent Neo and Patrick Naylor, all from Imperial College London. My name is Simon McKnight. This research focuses on closed set speaker identification, which is a 1 of n problem in that there is a closed set of n speakers on which the relevant models are trained, and when testing, the most likely one of those is chosen. The state-of-the-art models in this field now tend to be based on multiple frames, or features taken from multiple frames, with X vectors currently the best performing. The features being tested in this research come from the modulation spectrum, which is also based on multiple acoustic frames. There has been a significant amount of research into the use of modulation spectrum features generated from speech for various purposes, including automatic speech recognition, ASR, speaker identification, speaker diarization, and speech enhancement, though in recent years, most modulation spectrum research has focused on the speech enhancement side. On the ASR side, the research has shown that the most important parts of speech for recognizing what is said lie in the 1 to 16 Hz range of the modulation domain. That research has very much been dominated by the temporal envelope, as human hearing has been shown to be significantly more receptive to that than to the temporal fine structure. Broadly speaking, the temporal envelope is like amplitude modulation, whereas the temporal fine structure is like frequency modulation. More recently, however, research in the area of cognitive psychology and on cochlear implants suggests that the temporal fine structure is more useful for identifying speakers than it is for recognizing what is said. This research aims to build on that to include the temporal fine structure to the temporal envelope features and identify the most important parts of the modulation spectrum for speaker identification. In this research, the generation of the modulation spectrum is characterized as a 4-step process. Step 1 is the usual short-time Fourier transform for the relevant frame size and depth. Step 2 involves finding the magnitude, either by taking the modulus or by using the Hilbert transform to convert to an analytic signal. Either way, the result is a typical spectrogram, and we refer to this as the acoustic domain. Step 3 then looks across a number of acoustic domains in a particular frequency band and applies a second STFT. Step 4 involves taking either the amplitude or the Hilbert transform, and if the instantaneous frequency, i.e. the temporal fine structure, are desired, then the Hilbert transform must be used. The features generated were then used to investigate the correlations and feature importances, as well as fitting machine learning models. In addition, we tested what the reconstructed signals sounded like with particular acoustic and/or modulation frequencies removed. The signals were restructured using the constant overlap Kohler principle and had to be prepended with a number of zeros to avoid bangs in the reconstructed signal. This research focused on 1-second modulation frames with 250 millisecond steps on top of wideband acoustic frames, 3 milliseconds long with 1 millisecond steps, which meant we ended up with 20, after applying the Nyquist frequency in both the acoustic and modulation domains, we ended up with 25 acoustic frequency bands up to 8 kilohertz, where we had a sampling frequency of 16 kilohertz, and 501 modulation frequency bands up to 500 hertz, all chosen so that each modulation frequency band is just 1 hertz apart. That meant for each modulation frame L, we have a matrix size 25 by 501 features. The data used was the TIMIT dataset, because although this was designed for ASR, it conveniently arranges the data by speaker and utterance, which facilitated the training and testing. There are 630 speakers in TIMIT, each speaking 10 phonetically rich utterances around 3 seconds long. 2 of the utterances, SA1 and SA2, are spoken by all speakers. The data was initially split into 468 speakers in the training set and 162 in the testing set, and this was used for the correlation and feature importance analysis. But because the other analysis required the same speakers in both the training and testing sets, the sets were rearranged so that the first 7 utterances of each speaker, including SA1 and SA2, were in the training set and the last 3 in the testing set. The research initially involved running pair correlations of each modulation spectrum feature against each other feature, and then one-way analysis of variance, ANOVA, on each feature against the output speaker. ANOVA was used as it enables correlation of continuous features against categorical outputs, though it ignores combinations of features. After that, feature importances of each modulation spectrum feature were calculated by fitting random forests on the data. Lastly, as the modulation spectrum features resembled 2D images, convolutional neural networks, CNNs, were fitted on the data. This slide shows the average modulation spectrum for a particular utterance for 4 speakers chosen at random in the first region, 2 male and 2 female. The F preceding the speaker identity in the first 2 columns denotes female, and the M in the second 2 columns denotes male. The rows are for particular utterances, so the first row, SA1, was spoken by all speakers, as was the second row, SA2. The third row has different sentences for all speakers. Inspecting this data, we see clear peaks in the modulation domain around the fundamental frequencies of speech, which for the 2 female speakers is around 200 Hz, and for the male speakers is around 100 Hz. For each speaker, the modulation spectrum is impressively consistent regardless of the sentence, and this is also evident in the other modulation spectrum graphs not reproduced here. More interestingly than a single value, F0 for the fundamental frequency, there are patterns for each individual speaker that would enable speakers with similar fundamental frequencies to be distinguished. This slide shows the Spearman's rank correlation between each modulation spectrum feature up to 20 Hz in the modulation domain. It shows strong correlation between neighboring features, which suggests that using filter banks in future research to reduce the number of dimensions should be useful. The wideband ANOVA correlations between the input features and the output speaker also emphasize the importance of the fundamental frequencies. The first 2 graphs show a strong peak around male fundamental frequencies at slightly lower values for the Hilbert envelope than for the amplitude envelope, but only very slightly. For the temporal fine structure, the third graph shows less strong peaks at higher frequencies, so not great on their own, but may provide additional information when used in addition to the envelopes. This graph shows the ANOVA correlation for the temporal envelope calculated using the narrowband acoustic frequency with 30 millisecond frames, and this is purely for comparison purposes. The peaks are not as clear as they were for the wideband acoustic features, as well as taking much longer to calculate and using more memory, which is why the wideband acoustic features were preferred in this research. This graph shows the feature importances generated by the random forest models. Again, they emphasize parts around the fundamental frequencies of speech, but they also have particularly large values in the 0 Hz modulation frequency band, which is not really clear in this diagram, but we had to cap the diagram at the level of 0.0002 to avoid the output being totally dominated by the 0 Hz modulation frequency band. Fitting the random forest and machine learning models on the data gave the results in this table. The CNNs gave significantly better performance than the random forest models, and for our purposes, the main point to note is that the CNN trained on both the temporal envelope and temporal fine structure feature gave better results than that trained on the temporal envelope alone, even though the CNN trained on temporal fine structure features alone gave very poor results. Overall, these results fall a long way short of state-of-the-art, which would get over 90% accuracy for this dataset. So the modulation spectrum features do not appear to contain full useful speaker information themselves, and so the next obvious step is to see how well they work in conjunction with standard features like MFCCs. So the main conclusions from this research are that, firstly, the range of modulation frequencies associated with the fundamental frequencies in the modulation domain is more important than the 1 to 16 Hertz range most commonly used in automatic speech recognition. Secondly, the 0 Hertz modulation frequency band contains significant speaker information, and this was evident both in the reconstructed signals and in the feature importances. And thirdly, although the temporal envelope is more discriminative among speakers than the temporal fine structure, the temporal fine structure still contains useful additional information for speaker identification. And this is all very much a starting point. The next steps are to see if using filter banks and discrete cosine transform DCCs in the acoustical modulation domains improve performance. Quite a lot of the previous research does use those, but we wanted to start from the more pure features. And the other next step is to test whether the modulation spectrum features give us good results as single frame MFCCs and whether using both together improves performance. And that is all for this presentation. Thank you very much for listening.